So last time, where we left off. So we left off at a 5-5. Well, we did 5-4 and 5-3, and those were based on, these were second law, right?
More second law stuff.
I know you guys are probably tired of the second law right now, but we got to keep doing it for now. So we are going to continue with it, but now we're going to get into some problems, like what you're actually going to, there was a little bit of that last time where we talked about it. Now we're actually going to get into like how the third law or second law plays into what you're going to be doing, like on your homework. So let's start here. So it says, while the Kelvin-Planck statement of the second law provides the foundation for the rest of this chapter, application of the second law to thermodynamic cycles is by no means limited to the case of heat transfer with a single reservoir, or even any reservoirs. Systems undergoing cycles while interacting thermally with two thermal reservoirs are considered from a second law viewpoint in sections 5.6 and 5.7, which we'll get to. Providing results having important applications. Moreover, the 1 and 2 reservoir discussions paved the way for section 5.11, where the general case is considered, namely, what the second law says about any thermodynamic cycle without regard to the nature of the body or bodies with which energy is exchanged by heat transfer. In the sections to follow, applications of the second law to power cycles and refrigeration cycles and heat pump cycles are considered. For this content, familiarity and rudimentary thermodynamic cycle principles are required. We recommend you review section 2.6, where cycles are considered from an energy perspective with the thermal efficiency of power cycles, which I'll write those equations on the thing, but there, if you recall, it was eta. Eta was work cycle over Qn, right? So it was that. That was for power cycles, and then beta was the opposite. So that's what they're talking about, those equations that we used in a long time ago. So it says that we are going to essentially apply second law to those things right there. So 5.6. So this is second law aspects of power cycles interacting with two reservoirs. So it says a significant limitation on the performance of systems undergoing power cycles can be brought out using the Kelvin-Planck statement of the second law. Considering figure 5.5, which shows a system that executes a cycle while communicating thermally with two reservoirs, so it has two temperatures, right? It's hot and cold, right? A hot reservoir and a cold reservoir, and developing network, the thermal efficiency is the following. So essentially what it is saying is that what I just wrote was this. And obviously you can break it up into this equation as well. They are both the same. However, this does not give us the maximum performance, right? Because remember, second law, what we are trying to do is we are trying to find maximum performance and what things led to us not achieving that. And so that is what we are doing in this chapter, essentially, is maximum performance. So, maximum performance, this is not the equation for that. And we will talk about why it is not in the second and what the actual equation is. It says, we're going to skip down because we've already talked about this, where QH is the hot reservoir heat transfer and QC is the low or the cold reservoir heat transfer. It says if the value of QC were 0, the system of 5.5 would withdraw a energy QH from the hot reservoir and produce an equal amount of work while undergoing a cycle. The thermal efficiency of such a cycle would be unity 100%. However, this method of operation violates the Kelvin-Planck statement and thus is not allowed. It follows that for any system executing a power cycle while operating between two reservoirs, only a portion of the heat transfer can be obtained as work, and the remainder must be discharged by heat transfer to the cold reservoir. That is, the thermal efficiency must be less than 100%, which we already know that, right? We know it cannot be that. It cannot be 100%. So it says, in arriving at this conclusion, it was not necessary to identify the nature of the substance contained within the system, specify the exact series of processes making up the cycle, indicate whether the processes are actual processes or somehow idealized. The conclusion that the thermal efficiency must be less than 100% applies to all cycles, power, and refrigeration, although refrigeration is not efficiency, but it is a beta value. And it says, it applies to all of them. It said this may be regarded as a corollary of the second law. Other corollaries follow. So right here is what they were just talking about. This is figure 5.5, right? So what they were saying is that essentially, if you have 500 going here, right? Let's say this is 500 kilojoules, right? The work, essentially the heat going in has to be equal to the work and the QC added together. Because let's just say we had QH, let's say QH was equal to work cycle, right? That means that all heat transfer coming in went to work. That is not possible, as we have essentially shown, because then there would be no QC, which means there is no cold reservoir, right? So that means that it would be one hot reservoir to heat to work, and you cannot make, that's not possible, right? So that means only partially, part of the work, part of this heat transfer goes to work. So it could be like, let's say 200 comes out here. That means the difference has to be equal to the work of the cycle, which is then 300, right? But you can't have 0 here, 500 here, and we just make all the work ever, right? It doesn't work like that. So it says, since no power cycle can have a maximum thermal efficiency of 100%, it is of interest to investigate the maximum theoretical efficiency. So this is where second law comes into play. The maximum theoretical efficiency for systems undergoing power cycles while communicating thermally with two thermal reservoirs at different temperatures is evaluated in 5.9, with reference to the following two corollaries of the second law, called the Carnot corollaries. So Carnot corollaries. So Carnot, he actually had a big thing about, he was basically, so he did a lot of heat, basically stuff with cycles and heat transfer and thermodynamics, and you'll see Carnot brought up a lot. And it's called Carnot efficiency and Carnot cycles. Whenever you see that, that's who we're talking about. It's a scientist. I can't remember what his name was though, but I know his last name was Carnot. And then it says, these are the two corollaries. So the thermal efficiency of an irreversible power cycle is always less than the thermal efficiency of a reversible power cycle when each operates between the same two thermal reservoirs. All reversible power cycles operating between the same two thermal reservoirs have the same thermal efficiency. Okay, so what that means is that if you have an irreversible cycle, so something that has inefficiencies, it cannot be higher efficiency than the reversible cycle, the perfect cycle. And then it says all reversible power cycles operating between the same two reservoirs have the same efficiency. And the reason is because the Carnot equation is the following for power cycles. This is eta max, right? And what that means is that, so the reason why is that because in Carnot cycles, it only depends on temperature. There is no heat, it's just reservoirs. It's just the temperature of the reservoir. So if you have two cycles operating at two of the exact same temperatures, TC and TH, they are going to have the same efficiency because the rest of it doesn't matter. It is just at this. These two temperatures are the only thing that matters for a Carnot efficiency. So, let me see. We're okay with this stuff. Yeah, we've. I think this stuff's just too much. It's a lot more to just talk about that. Okay. So here we go. Second law, aspects of refrigeration and heat pump cycles interacting with two reservoirs. So, limits on coefficient of performance. So, we're going to talk about this first. So, the one we just talked about was power cycles, right? So, power cycles was what I just showed you, and they'll show the equations in just a minute. Now we talk about refrigeration cycles. So, it says the second law of thermodynamics places limits on the performance of refrigeration and heat pump cycles as it does for power. Consider 5.7, which shows a system undergoing a cycle while communicating thermally with two thermal reservoirs, a hot and a cold. The energy transfers labeled on the figure are in the directions indicated by the arrows. In accord with the conservation of energy principle, the cycle discharges energy QH by heat transfer to the hot equal to the sum of the energy QC received by the heat transfer from the cold and the net work input. This cycle might be a refrigeration cycle or a heat pump cycle, depending on whether its function is to remove heat or energy or gain it, right? For a refrigeration cycle, the coefficient of performance is this. So you guys should remember this from, I think, chapter 2 something. You've seen these equations before, right? So now we are going to talk about the perfect version of these equations, right? Beta max and this is gamma max, I'm pretty sure. If this isn't gamma, someone let me know. But beta max and gamma max are the two ones we're going to talk about. And also eta max was efficiency. So give me 1 second. Let me move down. The first one is a refrigeration cycle. So beta, the B, is for refrigeration. Gamma is for heat pump. And it says, as the network input to the cycle tends to 0, the coefficients of performance given by equations 5.5 and 5.6, which are these two right here, would approach a value of infinity. If W cycle were identically 0, the system of figure 7 would withdraw energy QC from the cold reservoir and deliver that energy to the hot reservoir while undergoing a cycle. However, this method of operation violates the Clausius statement of the second law and thus is not allowed. This method of operation, it follows that the coefficients of performance beta and gamma must invariably be finite in value. This may be regarded as another corollary of the second law. Further corollaries will follow. Okay. So this right here, this is either a refrigeration or a heat pump cycle, depending on what you want. So what happens is right here, this is the refrigerated space. We pull heat out of the refrigerated space. We send it to a compressor. The compressor then compresses it, and it becomes higher temperature. And then you get out here, which is the heat leaving at the hot reservoir. And then over here, it generally comes down through a valve or series of valves, and it comes back around to the first part. It's the fluid I'm talking about inside, not like, it's the fluid that I'm talking about. So the fluid takes in heat by heat transfer, pulls it into the system, and then does this cycle, and then does it again. But right now, we don't really care about what happens inside of this, right? I was just giving you some background information. We don't really care what's going on in here as long as we know these things, like the temperature and the heat transfer. Knowing what's going on inside is a chapter 10 thing. It's a refrigeration cycle chapter thing. So then it says, corollaries of the second law for refrigeration and heat pump cycles. So it says, the maximum theoretical coefficients of performance for systems undergoing refrigeration and heat pump cycles while communicating thermally with two reservoirs at different temperatures are evaluated in 5.9 with reference to the following corollaries to the second law. So it says, the coefficient of performance of an irreversible refrigeration cycle is always less than the coefficient of performance of a reversible cycle when each operates between the same two. So this is the same thing as power cycles, right? So we've basically talked about these already. But what it's saying is that beta must be less than beta max right here, or gamma max if it's a heat pump. And then it says, all reversible refrigeration cycles operating between the same two thermal reservoirs have the same coefficient of performance. So the same thing as before. If you have the two temperature reservoirs, one cycle operates at that reservoir and the other cycle operates at the same one, they both have the same efficiency. Because Carnot cycle efficiency and beta only rely on temperature and nothing else. Okay. Yeah, I don't think that we don't really need to talk about that. Yeah. I guess we can talk about this a little bit before we, this has been a short day so far because those two chapters were fairly easy. Not much to talk about there. So it says the Kelvin and International Temperature Scale. So everybody knows what Kelvin and Rankine are. But to evaluate maximum theoretical performance, you need to know temperatures in Kelvin and international scale. It does not work for other ones. So we have to know this. So it says the results of section 5.6 and 5.7 establish theoretical upper limits on performance of power, refrigeration, heat pump cycles. Communicating thermally with two reservoirs. Expressions for the maximum theoretical thermal efficiency of power cycles and the maximum theoretical coefficients of performance of refrigeration and heat pump cycles are developed in section 5.9 using the Kelvin temperature scale considered next. So, the Kelvin scale, I think you guys know what this is, so we're not going to go too deep on this, but essentially what it means is that it's this is okay, I'm really not going to spend a lot of time on this. Essentially it's just temperature in Kelvin, right? Is what we have to do for this. We have to have these temperatures in Kelvin for TC over TH. So right here I'm going to explain this part. So QC over QH, if you guys recall in that equation, right? 1 minus QC over QH, which was the efficiency of a power cycle, right? But for maximum efficiency, so eta max, I'm surprised I haven't showed these equations yet. It's 1 minus TC over TH, right? So what it is saying is that for a reversible cycle, so for a 100% efficient cycle, a reversible cycle, QC over QH is equal to TC over TH, which is why if you want eta max, you do it in temperatures. So it's TC over TH, 1 minus TC over TH gets you this. And they're the same equation, except if this is reversible, you use temperatures, okay? So, really fast. That is just a simple substitution. So if you're trying to find the maximum efficiency possible of a cycle and you know the two temperatures, you use temperatures in the efficiency equation. And you have to use it in Kelvin. You have to use it in absolute. So it's so essentially what you do is, if anyone doesn't know, Celsius to Kelvin is add 273. Right? So Celsius to Kelvin, you just add 273 and you end up getting Kelvin, right? And I guess I wrote that equation wrong. Celsius plus 273 gets you Kelvin, okay? And likewise for Fahrenheit to Rankine, you will have plus 460 gets you to Rankine. And so you have to use these temperatures when you go and use this equation for these TC and TH. You have to use them, and sometimes they won't give it to you on that. I had a friend that we argued after an exam one day, not in Thermo 2, but in another class where we had to do this, and he got an answer that I said was wrong. I was like, there's no way that's right. And he was like, no, I used the equations and everything, the TC and THs and 1 minus and all that. And I was like, yeah, you realize it has to be in absolute. It has to be in Kelvin or Rankine. And he argued with me for about 40 minutes until he finally accepted he was wrong and said I was wrong the whole time. I was not. And so here we are today. Now he works at a nuclear power plant, guys, so hope you feel safe. But moving on from that, essentially it says, let's move here. If the reversible power cycle were operated in the opposite direction as a refrigeration or heat pump cycle, the magnitudes of the energy transfers QC and QH would remain the same, but the energy transfers would be oppositely directed. So, like I said, I don't need to go super in depth into this. I think you guys know the difference between Celsius and Kelvin and that stuff. I think we're good on that. Yeah, this is all stuff just talking about temperatures. Yeah, this is really weird that they spent a lot of time talking about that. So, let's do another question. I'm actually going to do another question and then we'll call it early because 5.9 is we're actually already over to what we needed to do today. So we're going to do another question really fast. If I can't find one, then we'll just call it early today because there's just a lot of stuff you have to remember in this chapter. It's very long. So let me see. If you guys have any questions, let me know now. Like maybe I can, help you guys on that. Let me see if this is. Lecture problem 1. I don't think that that's super helpful. Yeah, okay, let's do this one then. We'll just use this example, and then we will move on for the day. So, let's go ahead and do this. So we're moving into the next section just to give you another preview of what we're going to be doing. Let's go get a Paint 3D out. So, as usual, open up our handy dandy Paint. Although these questions don't tend to be very long, so this one will be fairly fast, I'm sure. So it says, an inventor claims, so be careful when an inventor claims anything, to have developed a power cycle capable of delivering a network output of 410 kilojoules from an energy input by heat transfer of 1,000 kilojoules. So I'm going to go ahead and do what we always do. This is what everyone should do, is that we should start the exact same way. And how we start is we do this. Make ourselves a little text box. Although you guys obviously different, we write our knowns, right? Knowns. So it says, an inventor claims that we have a power cycle, so it is told us it is a power cycle capable of delivering net work of 410. So they have given us work of the cycle is equal to 410 kilojoules. That was the first statement they made. And then it said, for an energy input by heat transfer of 1,000 kilojoules. So that means we have Qn or QH, I guess whichever one you're more familiar with, is 1,000 kilojoules. All right. And then it says, the system undergoing the cycle receives heat transfer from hot gases at a temperature of 500 Kelvin and discharges energy by heat transfer to the atmosphere at 300 Kelvin. Evaluate this claim. So we now have to evaluate his claim. So they gave us TC and TH. So that's the next things they gave us was TC, which was 300 Kelvin. And they gave us TH, which is 500 Kelvin, right? Simply put, they just gave us the hot and cold temperatures of the cycle. So this is what we know, okay? And if you see down here in the corner, which I will scroll down just a little bit, you can see this. So we have Qin is 1,000. Q out, we don't know. What the 300 is the lower temperature, 500 is the highest temperature, and work of the cycle is 410. So now what we have to do is we have to evaluate whether this claim can ever be right. So how do we start this then? We did a little bit of this last time, but how do you guys think we can figure out whether this guy is an absolute liar? Who would think? I mean, I don't know. Do you think he's lying? I haven't seen this question. I have no clue. Like somebody posted the "Why you always lying?" guy in here. I have no clue. But we're gonna evaluate it. We're gonna try and figure it out if he's lying or not. So how can we do that, right? Very simple. We can start doing things like this. So I just know that these are the equations we have, right? Which is QH minus QC, right? That's one equation. We have eta is equal to work cycle over Qn. And this is for power cycle, by the way, right? All for a power cycle. And then that also equals, I'm just going to write the other form of it in case we need it. Right? So these are the forms of the equations we have. I'm going to go write another one as well. So we remember this one. This one is eta max is equal to 1 minus Tc over TH. Okay? So these are our equations, right? This is what we have to do today. These are the things we have in our tool belt, right? So we can use any of these equations to figure out what we need to do. So, how do you propose that we start something like this? Anybody? So Tanner's got us here. Let's see what he has for us. Let's see he has it planned. Calculate the efficiencies he says he can get. I agree. So we need to find out on his cycle, the one that he described, what is the efficiency he has, right? Like what can he get? So how do we do that? Well, we have work cycle, we have QH minus QC, we have this equation. So this is the one we need to use, right? So you're saying we need to use eta is equal to work cycle over QN, right? So Tanner, this is Tanner's idea. It is your idea now. If it fails, it is all on you. So, Tanner's idea. Sweet. So, Tanner's idea. We have work cycle, right? We were given that as 410 kilojoules. We also have Qn, which is QH, I guess we could call it, as 1,000 kilojoules. So obviously, if we wanted to find the other thing, if we wanted to find QC, could we do that? The heat transfer at the lower reservoir. Could we find that? Anybody? The low heat transfer, or the low temperature heat transfer. You could find it, but do we need to? Tanner says no. And the reason why he says no is because the power cycle efficiency is work cycle over QN, or it's 1 minus QC over QH. So you could do either one. And so I'm going to do both of them just really quickly because, just in case somebody feels more comfortable with one versus the other, I will do it. So I'm going to do it on the old calculator real quick, although I'm pretty sure I could do this one in the head, but you know how it is. So we have work cycle. So let's go ahead and write this down as 410 is equal to 1,000 minus QC, right? So you add QC over, you subtract off 410, and you get 590. Fairly certain about that one. You get 590 on the other side, right? So 590 is equal to QC, right? So Tanner's idea lives in all of its glory in here, right? And then there's one more thing we need to find. Because I did the long way, Tanner was not about that life. So we're going to go ahead and find the efficiency of his cycle, which is work cycle, which is 410 divided by 1,000, right? And so that should give you, what, like 41%? Yeah. So 41%. 41%, right? So we have his efficiency of his cycle is 41%. Now, I'm going to go ahead and that is now there. It's set in stone. Now we need to find something else. So who do I call on here? Can I call on Michael? Can I call on your child to answer this one? You think he's got it? He or she? I'm going to guess no, it doesn't have it. Okay, so how about this? Now that you've baited yourself in by I can hear that you're there, you can get the next part. Michael's idea. So what do we do next?
I've been preoccupied with my small child. He's only 5 months old. The man's a lot for me. I just try to do my best to pay attention and listen in.
So how about this? Let's break it down then for you. So what we have found so far is we have found the efficiency of his cycle, the one that he claims is correct. So you always do your research because this guy could just be a dirty liar, a snake oil salesman, right? Selling you volcano insurance in Southern Illinois. So we need to be sure that his cycle is correct. It's actually possible. So if we need to find something that is actually possible, how could we tell if this cycle can't work? Like how do we find out if this cycle is even real? Can it work? Anybody have any thoughts? This is Michael's idea though. But you can phone a friend if you need to.
Do we check to see if it's reversible?
Yes. So you're saying is that we need to find out essentially what the reversible cycle's efficiency is, right? To see if this is reversible, or if it's irreversible, or if it's fake, right? If it can't happen. That's the plan.
Yeah, because we did that last class.
Yes. So let's do eta rev. So this is the reversible cycle's efficiency, right? And the eta max, I guess you could call it that. I'll keep consistent. So eta max. So remember what I said is that eta max only depends on temperature. It does not depend on anything else. We'll get into more what Carnot cycle actually on an actual like TV or TS diagram, what it actually looks like. But for now, just focus on that. The maximum efficiency of the power cycle only relies on temperature. So we need to know the two temperatures, right? Between the hot and the cold. And luckily for us, the possible snake oil salesman has given us those two temperatures. So we have 1 minus, and this is TC over TH. So the cold temperature is 300, TH is 500, right? So we have this to deal with. So 1 minus 300 over 500. And the calculator is here today, guys. So I'll have to mark another one in the attendance book. So this right here is 2/5. If anyone wants to guess at that. So what that means is, what is 2/5? That is 40%, is it not?
Guess what I got.
So, Michael, tell me something here. Is this guy a dirty, no good, rotten liar? What is...
It have to be considered 41%, is that correct?
Yes. We got 41% on his cycle, right? And the maximum value we can achieve with those two temperature reservoirs is 40%. So this guy is a liar, and I'm going to see if that's what the answer they get here. So, as you can see, they fall it down. The first thing they do is they insert their values into the eta equation, which is work over Qn. So we get 41% here. Now let's move down. The maximum thermal efficiency of any power cycle can have while operating between two reservoirs at TH and TC 300 and 500 is the following. It is eta max is 1 minus TC over TH. If you plug those in, you get 40%. And then it says, in very nice terms, although not the ones that I did, but their terms were, the Carnot corollaries provide a basis for evaluating the claim. Since the thermal efficiency of the actual cycle exceeds the maximum theoretical value, the claim cannot be valid. I like my way of saying it better, that he is a no good piece of garbage that lied to you. But don't worry, we saw through it. We don't let it get to us. We saw through it, and he's a liar. So his thing does not work. It failed the Carnot efficiency test. And so he needs to go back to the drawing board or sell used cars. I don't know what he wants to do. But engineers, we're not falling for that. Does anybody have any questions about how this worked out? Because this right here is what you'll be doing on your first questions on your new homework. This is it right here. It's going to tell you things like this, and you are going to have to tell us if it's possible or if it's not. If it's popsicle, it's possible, guys. So, any questions on that? Any at all? Because if not, we are done for the day, and we are going to go into more, I guess, difficult questions. Not really difficult, but more in-depth questions. By the way, this right here, before we go, these are the equations for heat pumps and refrigeration. So refrigeration and heat pump. And they only revolve around temperature as well. So TC and TH over TC, TC, TH over TC. Or TH over TH minus TC. So these are those as well. So if you get a heat pump cycle or refrigeration cycle, you have to use these equations. which should be in your homework. And we will talk about this next time, but we're already over time. Like we are into the next part that we don't need to be talking about quite yet. But I'm gonna go ahead and take attendance. Hopefully that was clear-ish. I know this chapter has a lot of it's a lot of words. I know that it's very wordy, hard to follow at times because they use a lot of like equation talk. You know, they use a lot of weird speech to get across the points instead of just saying like it's not possible. They say things like, they say it in the corollary speech, which is sometimes confusing. So I just want to make sure we are somewhat understanding here. Calculator was here today, and Grant not. So this right here is it. You guys are free to go. Let me go ahead and shut this